start right on time because this room has been already filled before. It's a great privilege to have Dieter Fox here, and Dieter is a household name in robotics. I think probably most of us have read or have his book with us. He has done some of the foundational work in robotics, so I'll not go into what all he has done. I think probably these are the foundations of like Robotics 101 that we read in every robotics class. And of course, Dieter has won all the awards. I see the list, but I don't feel like speaking because it doesn't leave any award or any kind of fellow. So IEEE fellow, AAAI fellow, ACM fellow, etc. But I maybe a bit of trivia about Dieter. So despite being one of the supreme figures in robotics, Dieter is very down to earth. I met him as a PhD student in a conference, and he was just hanging out. I was like, oh, this seems like Dieter Fox. I've only seen in photos. And I went there, and he was gracious enough to give 30 minutes of his time in a busy conference. So I highly appreciate everyone who see Dieter around at a conference. Go and talk to him. He's not. he's too nice to decline talking to students.
For a drink.
And I don't think that's changed. And so with that, I'll hand over to give it over to Dieter to see what he has done today.
Thank you so much, and thanks for the generous introduction. It's always so great to be back. I did my postdoc here 25 years ago. I can imagine some of you weren't even maybe born yet. Oh my gosh, that's very scary. But I keep on coming back, and it's always exciting to see all the new work going on, see the new faces, and also this morning all the new buildings being built. It's very exciting times for CMU. And I can imagine many of you came maybe just because of the title, because there's RobotGPT. That seems to be a question that we as roboticists are getting asked like continuously right now, right? Where everybody sees these dramatic progress in language models, in vision models, and we roboticists are still having trouble kind of picking up whatever, a water bottle or something like that. I keep getting this question pretty often as well, so just like many of you. So I've been thinking a little bit about this. And today I want to kind of give a view of some of my thoughts on that topic, but also specifically, for example, we've been doing a lot at NVIDIA on simulation, and I want to focus a little bit on what kind of role I think simulation can play in this whole space. So as many of you might know, I'm kind of sharing my role. I'm half-time at the University of Washington in Seattle faculty, and I'm also leading the robotics research team at NVIDIA, mostly located in Seattle. So the work I'm presenting is kind of a mix of both of these works, and a lot of it is also collaborative between the two labs, but of course, most of it has also been done with great interns that we had over the years. So let me start with kind of the very high-level connection between, let's say, robot manipulation and the high-level topic of generative AI. I think we all agree that we're seeing really dramatic progress in the capabilities of, I'll just call it, I'm going to be very sloppy with the wordings here, like I'll just call it all generative AI, which are all these kind of models that we are seeing on, for example, large language models. Think about ChatGPT, GPT-4, vision language models that really have what you might call almost a deep understanding of images, but also purely generative models that are models that, for example, diffusion-based models that generate videos, images, and I think most of you would assume share the view that this progress has been really virtually impossible to predict, right? Like even people in these areas, when they saw these first, especially starting with ChatGPT, the progress has been dramatic, right? And people just thought that can't be. And by now, actually as a roboticist, we always used to say, well, these models, they're not really relevant to us because they don't do 3D and they don't do true planning and reasoning, and we all know there are limitations to what they can do. But the more I see this progress, the more I'm wondering, are we maybe just missing something on our end as well, right? Like, could it be that if we can generate some kind of data that these models are being trained on, but more relevant to robotics, I personally don't feel like I can predict what the limit of these models will be as we're moving on. So now, if you think about what really made these models so capable, I think it's a combination of, on the one hand side, especially the LLMs, they have just huge amounts of training data, right? Like all the text on the internet, trillions of tokens and words is the training data. And then, in a sense, if you have so much data in your training set, then most of these tasks that we throw at them that we call open world reasoning are kind of in distribution of your data set. So they don't even need to truly go beyond the kind of things they've seen in the data, right? So I think that's one of the key contributions here is having that data set and this large data available. At the same time, of course, on the model architectures, like especially these very large transformer models with now trillions of parameters, or even the open source models have hundreds of billions of parameters, also are just capable of learning. The more data you give them, the better they get, right? And that is also something that really came up with this data scaling and then capability scaling. So there is still not, with these data sets, also not so much on the overfitting actually going on. And then, actually from a robotics perspective, it seems like the training objective for many of these models is just very simple, right? It's kind of behavior cloning, which means for the language models, you put in text, a sequence of text, and then it just spits out the next word, right? So in robotics, we do something actually very similar when we do behavior cloning imitation learning, where you get demonstrations of sequences of sensor data or state information and controls. And then what the model just learns is, based on a history of those, what should be the next control that the robot should generate. So it seems like very nicely matched to supervised learning also that we might want to do in robotics. Now, so far, I think it's fair to say that we really haven't seen the kind of capabilities in the robotics domain, especially also as it comes to, and I'm going to focus today on robot manipulation. And here being at CMU, of course, it's Moravec. He saw it all coming, right? He always said that this paradox that the things that we always feel like are difficult for computers, such as playing chess and Go, like the holy grail of AI, these are the really difficult parts. But it turns out that those are the relatively easy parts for computers. What's really hard is the stuff that we humans don't even think about, like physical interaction in the world, right? Like picking up objects, moving around. The things that we do subconsciously are the kind of things that turn out to be really difficult also for computers that control these robots. And I think, of course, in addition to the fact that robotics is just difficult, which is kind of an excuse we can always use, I think the other one is really we just don't have the data yet that people had access to for their language and vision models. So that is, from my perspective, the big open question, right? So my hypothesis for today is I would claim, and I'm not 100% fully behind all of this, I'll tell you a bit more about it, but if we could generate really, really large-scale data sets, right, that are suitable for behavior cloning for robotics, kind of like the text data sets for language models, then if we combine that with these really capable Gen AI models, be it diffusion models, transformer models, then I think we can really try to teach robots these broadly applicable manipulation skills, and doing so just by, let's say, behavior cloning. Okay, the caveat here is I'm not trying to claim that that will be the end of robotics and everything is going to be solved, right, or anything like general AI, but I think if we could do something like that, at least the robots that are trained that way would be at a capability level that is way beyond the capability level that we're seeing right now. I think right now we're still very limited, and even with behavior cloning, I hope that we can get them to a level up such that then follow-up techniques like reinforcement learning and things like that can be actually very successful as well. So the big open question, of course, is for this is where are we going to get that kind of data from, right? So it has to be kind of temporal data. It has to be data annotated with actions and things like that. So we're all seeing many videos these days also on success stories where people use behavior cloning for manipulation already. And the underlying technique is a lot of kind of using diffusion kind of policies. And these techniques are trained on often human teleoperation, where they show the robot what to do, and they give it multiple demonstrations, and then the robot autonomously replays those demonstrations, right? And the capabilities are very, very exciting what you can see sometimes, right? What these robots can do. There's tasks related to cooking and things like that. I think one key limitations that we're seeing actually at this point with all these demonstrations is if you think about the vast space of things that we want a robot to do, that all of these are kind of teeny tiny point solutions in that space, right? Which means they are all these demonstrations and different tasks, they are isolated kind of demonstrations, and we're not seeing the kind of interpolation or cross-task generalizability that we would actually like to see and that we need to see in order to really see the robot capabilities of the next generation, right? So many of these demonstrations, if you look beyond just what's shown in the videos, but you look a bit more at the details, then often it turns out that, for example, if the robot picks up an object, it looks really impressive in the video, but it turns out that that object is not allowed to move at all, which means if you move the object, that robot is not going to be able to pick it up anymore. And for us humans, that is totally counterintuitive, right? If you think, if I can pick up this object and it moves 10 centimeters to the left, I should be able to pick it up too. But many of these behavior cloning kind of techniques, at this point, the way they are being trained on relatively small data sets, don't really generalize very well. There's other examples, for example, where if the table height in your test environment is different than the table height in your training environment, then your robot might not be able to pick up the objects anymore. So there's still clearly limitations, and I think these limitations are mainly also just because of the scarcity of training data that we have. So now what are different kind of ways that we can use to generate data for behavior cloning? On the one hand side, one exciting direction I actually think is using videos observing humans doing these tasks, like learning from YouTube videos or like Ego 4D kind of data sets where we also show how humans perform tasks in the real world, using also egocentric video, for example. And there's a lot of exciting work going on where then, for example, you can track the human hands and you can use that as a guidance to, like, for either as a reward function or as a high-level policy so that your robot can replicate that. At this point, my sense is that the gap between those videos and what a real robot would do in the real world is still a bit too large to actually succeed, but I think that's actually a very promising direction. The other example is what I also showed on the previous slide is real-world demonstrations. I'm sure all of you have heard about like the Google ARM farm and the data questions that went, for example, into the RT2 model training. More recently, there have been across institution attempts at combining different data sets collected at different institutions, like OpenX embodiment, and then the Droid data set is a very recent one. I think these are very good for pre-training at this point, but my experience is that, for example, with the OpenX embodiment is that the data sets are still too separate from each other, and it's really hard to kind of learn skills that go across these different data sets and things like that. So there's still a bit of a way to go. The Droid data set is more focusing on a single platform and a very controlled setup, and there's a higher chance of actually combining all this data into a single model in a meaningful way. But I think overall, all these data sets still, if you look at individual skills, they tend to overfit to very specific tasks. So the question is, how far can we scale that, right? If we look at a lot of the humanoid companies right now that get like hundreds of millions of dollars of funding, they will actually spend a lot of that money, I assume, also on generating teleoperate training data. So I think that'll be very exciting, and it's, from my perspective, it's a truly open question of how far they can go with this. One question, of course, for the academic research community is how we're going to get our hands on that data set, right? Because, of course, it's not necessarily in the interest of these companies to share it with everybody. Another alternative to this kind of very expensive kind of data generation is simulation. There's various different environments, various different skills. The advantage of simulation data environments is, of course, once it's set up and everything, it's relatively cheap, and you don't have to be a robotics expert to run these experiments. One key problem with these data sets is, of course, the sim-to-real gap, that many of them, the physics don't really work quite as well as they should, so that what you learn in sim, for example, transfers to the real world. And another open question is really asset generation, like how do we populate these in simulation environments with the right kind of assets and tasks. And I will talk a bit more especially about this sim to real gap. So in the next section, I want to give you some examples of the work that we've done, especially also at NVIDIA, on kind of training manipulation capabilities in simulation so that they transfer to the real world. The simplest thing you can do is, for example, you want to teach a robot how to grasp objects. Right? Let me just give you this one example here, where you have a 3D model of the object, and you want to generate a data set, a labeled data set, that says which are good ways for picking up this object. Right? Let's the phone here, for example. What you can do is you can do very simple rejection sampling on this, which means you have a 3D asset of the object, and you just randomly guess possible ways for how the gripper could be relative to it. And then you feed that into a physics simulator and tell the physics simulator, okay, close the gripper and move up and down. And for some of the grasps that were random good guesses, it's going to work. But for many of the grasps, it doesn't work. And what you're going to do is you're just going to retain the ones for which the object remained in the gripper. Right? So that's actually a very simple way of generating now for this object and this kind of gripper a data set that contains all the kind of promising grasps for picking this object up. Okay? You can do this for different combinations of grippers and objects. And here we did this, for example, for a subset of the ShapeNet data set, where we have almost 9,000 objects, and we ran them all through this parallel physics simulation in order to figure out the good grasp. And now what we have is we have a data set of annotated objects with grasps, right? The next thing we can do now is that I'm not going to go into any of the technical details, but we had a line of work where we can then use that data set in order to train a deep network. Initially it was like a variational order encoder. The most recent work here is the M2T2. Collas here is like a transformer model. But the idea is that you can now, in simulation, you can just generate random scenes, let's say tabletop scenes or scenes with drawers. You can put these objects in the scene, and you can label also the scene with the grasps that were successful on these objects. So the input, and then what you can do is, you have this scene and you can render it as a point cloud, for example. Okay? So in simulation, you're not using the shape models themselves, but you render it as a point cloud, because that is what the robot will observe in the real world. And then you train a deep network that takes as input a point cloud, and the output of the network is, what are all the possible ways in which I could grasp these objects in the scene? Okay, like you can see this illustrated here on the left side down there. And in addition, in this specific case, you could also train it to say, if the robot has an object in a certain configuration in the hand, what are the possible ways in which it could place it in the scene? Okay? And it turns out that that works surprisingly well, especially on point clouds. Point clouds transfer pretty well from sim to real. One other aspect that we might want to look at then is, for example, object segmentation. And this is work that we started kind of parallel. Of course, nowadays you might use SAM, segment anything, for this, which was trained on a huge amount of real-world data. But here I just want to show that we can also do actually capable segmentation training purely in simulation. So this is just some example where we randomly generate scenes with objects, and the objects can come from different data sets, and then render them. And the nice thing about simulation is that you can get this segmentation and everything for free. Right? We also, in this line of work that's called Object Seeker, we can train a network that then says, I give you an image of an object, and you should detect the segment in the scene that corresponds to that image. Okay? And that is purely trained in simulation, and let me just show you an example for how that then works. So here is on the upper left, you see that's kind of the query view where you say, okay, I have a picture of that pot. On the next image up there in the middle, you see that's the view from an external camera, and the upper right is the view from the gripper camera on the robot, which is just up here. You can see that. That's the scene. And so the idea is that what the model takes as input, it takes that query view and the the image itself and then uses the query view to segment out the object that this corresponds to. In this case, it's a screen mask that we can automatically then generate. And then we feed that together with this grasp network that was used to generate these grasps. And then the robot can pick up the object using one of these grasps. And also in this case, even, let's say, there was a network that was trained to do collision checking, because collision checking in some settings, for example, if you have occlusions and things like that, using just the point cloud might not be as robust as, for example, training a deep network to do collision checking for you. Okay, here's another scene. So again, here in this case, we just give it the image of the fruit snacks. You can automatically segment it out and then generate the grasp for that. All the components, everything is purely trained in simulation. And the nice thing is, let's say, compared to some of the earlier work I was hinting at, is that, of course, in these simulations, you can nicely randomize environmental parameters, right? Like the size of drawers or the height of countertops and things like that. So the system then becomes robust to that as well. Wait, there was one. Yeah. And then once you can pick up this object, this is work we did last year, it's called a proc prompt, where then that's one way now to connect these kind of, let's say, low-level capabilities with this vision language model. This was with GPT, where the idea is we have the language, we want the language model to generate Python code that the robot can execute, right? And here's just one example where the input to the model for the prompting is we first give it an action of what the code structure should look like. For example, from actions import, so we can say these are the actions the robot can actually execute. Then we have a function, for example, that says throw away banana. And also importantly, the object. So we tell the code or the LLM what are the objects that are accessible right now in the scene. And then we want to use that to define a function. And then in this context, for example, if you look at the left scene, the key question is always how do we enable the robot to do this, what's called open world reasoning, right? That is the key reason why we use LLMs, because that's its capabilities to reason about things that are not pre-trained on a classified set of objects, right? So for example, you might then say sort the fruits on the plate and the bottles in the box. We can now take that sentence, generate a function that we would like to have specified in Python. Then we run a vision model to detect the objects in the scene. So this is now also input to the LLM. And then we tell the LLM kind of, OK, now give us the individual steps of that, right? And then we can just execute those on the real robot. Okay? I'm not making claims here that this is doing really complicated planning or things like that, but it's kind of what you might consider like a very loose connections between VLMs and robotics, where you have very specific robotic skills, and the VLM then can call these, right? And of course, we all know all the limitations to these kind of work still, where it's about hallucination and things like that. But it's just an example how you can combine these kind of skills now. All right, so so far the manipulation setup was mostly kind of object pick and place, so relatively simple from a physics simulation perspective. Another area that we've been looking at is what we call context-rich industrial tasks. Okay, it turns out that most of these hard context-rich tasks in industry are still being done by humans because robots are just not necessarily, for example, flexible enough to do these or do them especially when the environment changes and things like that. And NIST, for example, this is not the most recent version, but they, for example, came up with a task board to benchmark these capabilities. Like you can see here are these different assets, and they need to be inserted into something. And it turns out that all these tasks have been done actually typically on real robots. And even the benchmark environment was like a real physical benchmark. And the problem was that it's really hard to actually simulate that. I must admit, I thought, come on, that can't be hard, right? It's like really well-specified objects. You have good CAD models for them. How hard can it be to simulate sticking a peg in a hole or something like that? It turns out it's not trivial to get it to work well. So for example, when we did this work, the first line of work was called Factory. At the time, the state of the art was something like this, where they were able to simulate threading a nut onto a bolt, okay? But the problem was, first of all, the margins were not quite the margins that we would see in real physical nut-bolt setups. And also, the simulation was 350 times slower than real world, which from a learning perspective sometimes beats the purpose of simulation, because the reason to do one reason to do simulation is just that you can do very fast simulation, faster than in the real world, right? So, but that was kind of the state of the art, and then we worked at NVIDIA with people also from the physics team, and they did some magic tricks on that, because they hadn't considered that use case beforehand. So we said, well, that's actually important for these industrial tasks. So they then came up with a simulation that can now do, of course, doing some magic on the GPU and some optimizations. So now they were able to actually simulate 1,000 of them in real time in parallel. So beforehand it was a single 350 times slower, and now we can do 1,000 in parallel, right? The nice thing is, once you can do that, you can start doing learning in this context, right? Because you can do reinforcement learning for that. And then you can, for example, start training a policy for doing this task in simulation. Okay? Here's just one example that is actually the most recent work in this line, where now in the automate work, Yash and his team and Bingxie, she's an intern with us working on that, where they defined 100 of these insertion tasks in simulation. And then typically what we do is we train using PPO, individual policies for the different tasks. Some of them are kind of threading, some of them are insertion tasks. And the policies first are trained typically, let's say, for each individual task, you have a different, what we call state-based policy, which means you give it access to the internal state of the simulator, the exact pose of objects and things like that. And then we distill that into using that as training data to distill it into a policy that operates, for example, from point cloud data. And I'm not talking necessarily about point cloud observations, but point cloud representations of the assets. And then we're getting on these policies, on the individual policies, for example, we're getting very nice success rate both in simulation and in the real world. So on the right side is what these policies now do on the real world. We do zero-shot sim-to-real transfer on those. So it's actually working very well now, I think. One thing is, and then instead of just doing these individual policies, of course, nowadays, you can then use the data to try to distill it into a generalist policy that can do it independent of the individual assets. And it's not quite where I think we would like it to be ultimately. So in this case, for example, we were able to train a single policy on 20 different tasks, different assets. And the success rate, if you look at the numbers here, surprisingly in sim actually drops by 10%, but the real world doesn't even drop that far. But still, what you would like to see is, of course, that you can generate enough tasks and then distill this into a single policy so that you get really cross-task benefits, right? So that, for example, you get a policy overall that's better than any of these individual pre-trained policies. And also, ultimately, of course, you want to have a policy that can work on unknown assets as well. We're just getting there right now and starting to look into that. Okay?
So I have a question.
Yeah.
So the first question is, did you randomize the physics parameters? And the second is the policy you distill to a recurrent policy, or it's a...
Yeah, it's a recurrent policy. And I'm pretty sure, but I'm pretty sure they did not, for example, fine-tune any physics parameters per task or something like that. There was just once, if possible, the fine-tuning. And then, of course, you do, in addition to make it robust, you do some randomization on the physics parameters as well.
How do you get point clouds here? Is it through that video sense camera on the arm, or the multiple cameras?
So in this case, actually, the point cloud is not for the sake of, let's say, like what Pulkit, for example, did for the object. It's more like a point cloud, because, for example, if you want to have state-based policies for different assets, the problem is you can't learn a single state-based policies across assets because the state, which means the position of the object, doesn't convey actually which object you're holding in your hand, which means you can't learn a policy that adapts to that. So in that case, we replace the state by extracting a representation from the point cloud, still in simulator, from the point cloud that represents the asset itself. It's not coming from, let's say, a camera observation or so, right? So it's a complete point cloud of the asset.
Multiple cameras around.
At test time we have, I don't know, I think it might even be one camera. And with the camera, then we do object detection because we still assume we have the asset, right? And then use that as the initial post, but then generate the point cloud again that goes in the policy. But you can well imagine that.
So you fit the asset to the real world and then you point out from that. Or is it
The asset, we still assume that we have the asset even in the real world, and we take the asset point cloud, but we're using the pose estimate to place the point cloud relative to the gripper. But the relatively obvious next step is to learn all of that just purely based on observed point clouds.
Can you please comment on the accuracy of the state estimation at the current time, or that's the
I'll talk briefly about state estimation. Where is it? In 2 slides, yes. Another step now is, for example, tactile simulation. So this is some experiments we did with the gel site. It has it generates a tactile image on this pad that is between the grippers, or on front of each of the gripper. And on the left side, I'll show you here, for example, this is a simulation rollout of a policy where in the lower left, of course, you see the gel site image that we can generate very fast in real time, or faster than real time in simulation. So now again, we can start doing simulation training using, for example, tactile information as well. And we're also looking at using force feedback and things like that as well. And then you can do, of course, these kind of experiments nicely, where here's kind of the training success using PPO on that, where in green we have the training curve and success rate that we would get if we give the policy the ground truth position of the peg, which in reality, of course, you never have. If we now perturb that estimate with some noise that the system doesn't have, then actually PPO doesn't succeed at all. It's kind of the grayscale that is the flat line at 0. And then these other three, the blue, orange, and purple curve, they show training results if you use either a gripper, a camera that is placed on the wrist of the robot, right? Because that gives you information about the object, where it is relative in the gripper. This would be the purple curve. And then if we use the tactile image, this is the orange curve, which is very similar, but actually combining the tactile image and the wrist camera image gives us the blue curve, which is better than those. So it kind of indicates that, of course, combining these different data sources into a single policy improves performance. Again, the nice thing about the simulation setup, we can start making all these kind of experiments, right, and really benchmark different things against each other. We are also now getting this to transfer to the real world, which means we can, with zero shot, we can train a policy with tactile feedback, and then it works in the real world. And it's just to highlight that, yeah, it works in the dark if you have a tactile sensor. All right, so this is kind of for this line of work for, let's say, more industrial kind of manipulation tasks. But I think ultimately, even our robots, right, they should be able to plug something into a power outlet or something like that, or USB and things like that. So I think all this kind of can lead to these kind of capabilities as well in the open world. Beyond, let's say, these more static simulation tasks, of course, I'm sure many of you have seen this line of work, the Dextream, where this was Ankur Handa and his collaborators did in-hand rotation of objects. And in this case, the interesting aspect was, I don't want to spend too much to explain the task, but it has to rotate this object to a certain configuration. And here he trained actually a state-based policy And in order to successfully execute that state-based policy in the real world, he also trained a key point detector for the cube, for example, that then can be applied in the real world to give you the state. So, and that key point detector was actually robust enough that we get also sim to real transfer, zero shot. Now, briefly, one example on the notion of pose estimation. It turns out, I believe in many settings, 60 object pose estimation doesn't make actually that much sense because many objects, like you don't have a model for them, and I think it's kind of an artificial bottleneck. But for example, you can imagine in industrial settings or so where you might have actually access to 3D models of your assets and things like that, pose estimation can still be extremely helpful. And this is just some work I want to highlight. That is, Bo and Wen did this at NVIDIA, and it's coming up at CVPR this year. It's called Foundation Pose, of course, Foundation. The idea is, let's assume you have a 3D model of your object, and textured, like the one up here. And this is for kind of local pose estimation. So you assume you can detect object with a bounding box or something like that. But the goal here is to estimate the 3D position and orientation of the object with high precision. Okay, so you have some kind of rough initialization, and then you try to estimate the pose. And if you can do that, you also want to do tracking over time by just initializing your estimator from the previous time step. So the idea here is this render and compare kind of approach, which is something we've also done before with techniques like DeepIM or Megapose. So the input is a rendered view onto the object, where the rendered view comes from your current estimate for where the object is. And it is also kind of a part of the image where the object is. In this case, it's the, is it the Cheez-It, I guess? Everything is either Cheez-It box or mustard or so nowadays. And then this is the input to the network. And then the network is just trained. Details don't really matter. But the network is trained to give as output a local translation and rotation of the object pose such that the rendered object matches the observed object closer, right? So it's kind of like, for those of you who know from depth cameras or ICP kind of techniques, this is doing something like learned ICP, but in the full image depth space, okay? And then the idea is you get a refined pose estimate, and then you can repeat that process by re-rendering your object at your refined pose and let your deep network suggest another predicted pose. And again, we've done this before, but now actually this is really kind of a really level up in the capabilities. And the key trick was really also again on just data scale, right? So Bowen trained this purely in simulation. We just have like the 40,000 objects from Observerse, and then also from the Google scanned objects 1,000. Then also we use some additional texturing to have more variability on the object texturing using, for example, an object and then an LLM, and it says, and the LLM might say, oh, the wine glass should be green or something like that, and then you have, it's called a text fusion that can generate then a texture on the object, and you get more variety on your data. And then, of course, in your training data, you do a lot of randomization on the lighting and everything to make it robust. And the interesting aspect here is first this initial estimation, if you don't have the pose relatively close yet, but you have to try different positions, takes a second, but then tracking can be done at 30 hertz with this network. And it's currently, it's state of the art on many of these kind of data sets that measure kind of 60 pose estimation and tracking. And the key thing here is that this network is trained, since it's trained on all these objects, it can do zero-shot object tracking, which means many of these previous works, they assume that you can train your network on the object that you want to track. In this case, the object is just an input to the network. Okay, I'll just give you some examples here. So on the left observation, on the right side, you see kind of a rendering of the object where the system detects it on the right side. So it's actually extremely stable and robust. And again, it's very, very precise. And also let me note again that these objects have not been in the training set of the network, right? So it's truly kind of zero-shot new object, and you can do that. That's where the name foundation post comes from, of course. Okay. One more example here on the left side, because for industrial stuff, these kind of objects like shiny metal pieces and things like that are actually very relevant, right, for many of the tasks that you want your robot to do. And we just have it here in front of the camera, and you can see that the tracking works actually very, very well without any additional training. Yeah?
Did you include RGPT or if not?
This is RGPT, I think. Yeah.
I'm testing as well.
Yeah. And here on the right side, this is, I think, where they built the model just maybe even with something like bundle SCF or so, but then you can see that the tracking is actually, even the lighting conditions are not great, but the tracking is very, very good. So why I'm showing you that is just to highlight that sim to real doesn't only work with point cloud kind of data, right, or depth data, but it's also getting nowadays better and better at RGB kind of sim to real. There was a question there, yeah.
That piece of metal has just like no texture, right? Other than just like a couple of uniform holes. So do you think it's actually using much of the color data, or do you think a lot of it is just using the depth? Because you give it both, right?
I think it's using, I would say it's using a combination. You can see there's, for example, also still maybe holes like that. And I mean, that's a nice thing versus, for example, key point-based kind of techniques, right? They always rely on visual key points that you can detect. And this system that is all just end-to-end trained doesn't require that. Sure. Who knows what it does internally, right? But so I don't have a clear answer in this specific case, but and it's very robust also, as you can see, actually with respect to occlusions and things like that, right?
Are these still YCB? Like, how do you get? Did you first create a model out of it? The real?
Yeah. So the idea is with these objects, there's different actually. You can look at there's different setups. One is, for example, in the left is where we actually have a CAD model, because for many of these industrial parts you have the CAD model that we can then use readily. And for some of those you can you can train it to do pose just based on multiple views onto the object. It doesn't actually require a full 60 pose of the object.
Yeah, that's what I mean. Like, if you can generate this 3 model from like nerves, anything or something, that means
it readily fits in. Yeah, totally. Yeah.
So does it generalize to?
Yeah. I think this might even be what they did in this case. Okay? All right. So now that, what I tried to convince you of is that simulation can work pretty well, right, for at least this set of tasks that we looked at. I'm not saying simulation can solve everything, but we're getting reasonably good sim to real transfer results, both on the physics and on the appearance of things. Now where we want to go with this, because so far all I showed you is kind of individual little projects, right, where we set up the training specifically for this and the assets and everything. And now I want to just describe like where I think we can go with more like setting up a larger framework for how to do that. And it's kind of like a sim-based robot training pipeline, right? Where the idea is there's like, in my view, there's kind of 3 key steps that we always have to do if we want to train these things in simulation. One is, first of all, if you have a certain task or so, you generate random assets and scenes, right, that represent whatever application domain you want to worry about. Then the next thing is we need to be able to generate certain tasks in this environment, and also could be rewards depending on how you generate your solutions. For example, in the industrial setting, we used reinforcement learning, so you have to set up your rewards. And the next step then is, for example, you go into these environments, and then because you're in simulation, you take advantage of the privileged information that the simulator gives you, for example, right? So for example, I know exactly where the objects are, I have the pose estimation, I have the perfect shape estimation. That's the key advantage that I have being in sim. And then it turns out that many of these techniques actually work very well. They can solve tasks in sim that we cannot yet solve in the real world. So that's a key trick. And then what we do is we just generate many tasks. We use techniques like task and motion planning or reinforcement learning to solve these tasks. And now what we can do is we can use these task solutions to do behavior cloning on them. right? Where the key trick now is to say, we take all these demonstrations, which is rollouts of the demonstrations, and then render these rollouts with the sensor information that my real robot will have access to, and then I can do behavior cloning, and we're exactly in this kind of world where we want to be, right? Just to be very clear about this, I don't believe that we will be able to do everything just in simulation, right? So clearly, adding and combining that with real-world demonstration data or even video data and things like that will be crucial on the long run. And then, of course, building what we're looking into, just building the compute infrastructure for doing all of this. Where do you store the data? What formats do you store the data in? We're using this USD representation for these simulation environments, and then also like how do you train these models. So let me just give you an example for what I have in mind here. So for example, on the scene generation, if you want to train a robot now to do more of these indoor, let's say, kitchen tasks, then we have a project that is looking at this programmatically, procedurally generating these kind of synthetic scenes of kitchen environments. The key thing to notice is that these are articulated scenes that also so that they work with a physics simulator. That's, of course, always the important part, right? And then, because we're in simulation, if you can do it with one, you can then randomize over that as well. It turns out that the variety that you can come up with these kind of techniques might still be limited, but at least now we have a large set of environments, right, that we can run in our full physics simulator. One question is then, how can we go beyond just these procedurally generated environments? And of course, we can leverage generative AI for going beyond these simple assets. And for example, Katerina is doing some really cool work in that domain. We're looking at, for example, 2 projects right now where, for instance, you might want to generate assets like cabinets and drawers and things like that. And you can imagine we train a system where the LLM says something like, okay, the cabinet has 4 shelves and 2 drawers. And then from that, actually, you go to a URDF description of that cabinet. You learn to go there, put that out, and then you actually have also shape models for the individual components of that. And then out, you might get like fully functional shape assets that you can then use in your simulator. Another line of work, my student Zoe did this. It's called URDeformer, where what she did is the following. She said, okay, I can generate, in this upper row, I can generate, let's say, procedurally simple assets for like doors and drawers and cabinets and things like that. She then figured out a way to use, and I'll point at the paper, to use stable diffusion so that you can render now actually pretty nice, realistically looking views onto these objects with a lot of variety in them. The key trick is that these actually rendered images are consistent with the URDF model with respect to handles and things like that, right? So that was one tricky piece. But now what you can do is you can train a deep network that goes the other way around. So for example, the idea is you can download an internet image of a kitchen, and you can train a transformer model that then goes to generate a URDF of that kitchen with all the drawers and doors, right? So, and also you can do this, it works even much better, of course, for individual assets like whatever, fridges and stuff like that. But the idea is now that you can download many, many images and just convert them into these assets that you can now feed into your simulator. And that means that the simulation environments will have far more variability and diversity than whatever you can come up manually, right? So this is not perfectly done. Then, of course, you can run your robot in these environments and do training in them. So the next step is if we have these randomized assets and scenes, the next step would be generating tasks and rewards. So one way to do this is kind of do it manually, where you place objects in them, and then you might say, hey, I want the objects to be in the drawer, or set the table and things like that. Another way is, of course, what we're looking at, and again, Katerina is doing some really cool work in that domain, is using LLMs to generate tasks automatically. So you can tell the LLM, for example, okay, these are the objects in front of the robot, just suggest some things the robot can do, and it turns out that they are surprisingly good at that. At the same time, you have to have techniques for filtering out all the noise, of course, that they generate. But overall, I think it's a very promising direction. So now that we have these scenes with assets and tasks, Currently, what we're looking at is using task and motion planning in order to generate demonstrations for how to solve these tasks. So that's a whole area that I'm sure many of you are familiar with, is kind of especially for robot manipulation. So it's a planning technique that works both at the, let's say, abstract action level planning, but also at the continuous and physics level planning. So for example, they reason about discrete state of the environment. For example, if a door is open or closed, so if the robot is holding an object or not. They have actions, they have preconditions for actions, just the classical kind of planning, kind of precondition kind of style, effects of actions. But then they also reason about, for example, if the robot wants to pick up this, can I find a continuous robot motion in order to move the gripper there, and can I place the object at a different location and things like that. So there's various very capable systems out there. We're using the one from Kalen Garrett. It's called PDDL Stream. And the key trick here is, again, these task and motion planning systems, they're not that great in the real world yet because they require access to the real world. But the beauty is we are in simulated environments, so we have access to everything we need. And that's why these TAM systems are pretty good. Let me give you just one example here. So for example, in this case, the task is for the robot to put the tea kettle on the stove somewhere and hold 2 teacups. I know it's not the most exciting task, but it's just illustrating where this is going. Okay, so we just specify the high-level goal, and then the planner does all the motion generation and everything for us. Okay, and once we have that, you can imagine that if we could generate thousands and thousands and thousands of these things and generate the demonstrations, we can now render the demonstrations with the kind of views that a real robot would get. Right? We're just simulating, for example, the wrist camera views. We get access to the state and everything. And then use that as the training data for our behavior cloning. Yeah?
The grasping pose of the manipulator change if we mention the cup is filled with water or tea.
Could you a bit louder? I didn't understand the second.
Yeah, would the grasping of the manipulator change if we, instead of just saying pick up the 2 cups filled with something?
Oh,
If there's liquid in there.
Yeah.
So,
If there's liquid in the cup.
Oh, well, that depends whether your task and motion planner has that modeled, right? At this point. So I guess you can imagine actually an LLM might be able to say, oh, be sure to hold it upright. They're actually capable of this kind of reasoning, right? But in the task and motion planning system, you need to explicitly have these kind of things modeled at this point. Yeah. Oh, one very quick, am I running out of time soon? I just want to give a quick plug in. You've seen in the previous animation that the motion of the arm was kind of a little bit convoluted, right? So we developed, I don't know whether people have heard of Kurobo, which is a tool we just developed. Bala did this, was an ICRA paper last year. But for example, with the standard motion generation planners, you can see here on the upper left, they often generate demonstrations, even in simulation, that are kind of generate this motion, as you can see here, that is kind of very convoluted, let's say, right? It's not a very natural path. The problem with the sampling-based paths is also that they are very hard to learn from for behavior cloning because there's too much variability in them. Here you can see another example. If you use this bidirectional RRT planner, for example. And what Bala developed with Kurobo is a technique that is fully optimized for GPU, and it generates actually plans. So it combines RRT-based sampling generation with optimization, everything. So the package is on GitHub. You should download it. It's much faster than the alternative techniques right now. So it's faster. It generates much shorter paths as well, better paths. And another key thing is it actually works with point cloud data, right? Which is one of the key limitations many of these other techniques have. Let me just give you one example here. Here's just a demonstration of the speed of the motion generation. So whenever it reaches the previous goal point indicated by the green thing, that is when it starts planning. Okay, so it's very fast in doing that. On the right-hand side, you can also do then kind of this reactive motion generation with this kind of framework. And we're integrating that, of course, with our demonstration generation as well, so that the demonstration that you give for your robot for the training are becoming more consistent and fast. We can generate them faster as well. And then finally, once we generate the data, all we have to do is behavior cloning. And there are now, as we know, there's just so many techniques out there, right? Diffusion, different kinds of diffusion policies. We have techniques that use transformer, 3D transformer kind of techniques. You could imagine techniques like perceiver actor that some of you might have heard of, or RVT is a recent technique. Katerina did some nice work also on Act 3D diffusion policy learning, but there's many techniques out there. So, but the idea is once we have that data set, we can train them on that data set and evaluate how well they do, right? Here's just one example. This is work. Murtaza, is he here? Oh no, he said he might not be able to come. But for Murtaza here, he did this during his internship with NVIDIA, where we actually were able to set up all these environments with full task and motion planning. Okay, so there's no manual human teleoperation data generation, but it's all task and motion planning, and use that then for behavior cloning training of a transformer model. And he got very good results, but now moving forward, imagine doing something like this with the kind of data that we could generate in these kitchen environments and at a much, much, much larger scale. Okay, that is kind of where we're moving right now. So now I'm coming to the very last section. So now that we have all this data, let's say, the question is how can we use it, or how should we connect it, for example, to these large language models, right? Because what the language models really provide to us is this open world kind of reasoning, right? They can provide at least some kind of guidance in settings that we haven't seen in any kind of robot training data or things like that, right? The question is, how do we integrate our robotics models with these large language models, right? On the one hand side is one way we could do this is the one on the left, which I would call loose integration, right? Which means we have our vision language models. You take your favorite, whatever, GPT-4v, and you just use this to give guidance to the robot. So it's becoming it's scene understanding and planner, and then we as roboticists, we train some skills, for example, pick up or place and things like that, and then the interface between that is just that the vision language model just calls the right skill. That is kind of what I showed when I showed this proc prompt work. It's kind of at that level, right, where we predefine exactly the kind of skills that robot needs, and independently we're just using the VLM to work with those. I think ultimately that's just going to be too brittle, and also the notion is that it's easy to come up with a small set of skills like pick, place, open, close, but overall I think the things we want these robots to do are not always easy to classify into these discrete set of skills. So another extreme is we just say, well, we'll have a big vision language action model, right, that takes in so on the left side, it's, let's say, text and images, because these models are not trained on robot data. But on the right-hand side, maybe we can use the robot data to train end-to-end, really full vision language action model that take as input images, any information about the robot state, history, and things like that, and they're literally output controls, right? This is kind of the RT2 kind of model, right, where they actually really output delta action for the robot manipulator. I must admit, I don't know, maybe, right? It seems from a robotics perspective, we often like kind of hierarchical kind of approaches, but I'll go on the next slide I want to talk about it, but that is one approach, and I think there's something in between where we're actually not just using these vision language models, but we're fine-tuning these vision language action models together with robot data so that they become better, but the output is not necessarily a discrete set of skills that we train with our robots independently, but the output is some kind of tokenized interface that we train and align with robot skills that we learn. So, and then what we have on the low level is maybe more like a policy that could be a diffusion policy or your favorite transformer-based policy that then we train for the robot to execute, right? So it's kind of between these two extremes, and I'll leave it to you, or maybe to the discussion on which of those is your favorite. So now, why or how could we even train these vision language action models, right? These not, in a sense, like not just taking these models as the vision and language people give them to us, but how can we improve on them, right? Because the insight is why I think there's actually hope is the following. So these LLMs, we know they were trained on these huge data sets, and they are extremely capable for the kind of tasks they're trained on. Then there are many vision models out there now that were also trained to provide very robust representation of image data, right? And examples, Dino, Clip, masked autoencoder kind of models. So the key trick of these models is that they were trained on very weak supervision that you can generate on huge data sets. And the representations they generate are, because of the size of the data set, are actually very, very capable. Let's put it this way, right? And they showed that you can very quickly adapt them on downstream tasks. So the open source community, if you now want to train vision language models, not just language models or vision models, is what they do. For example, what the Lava work does is the following. They have the language model as the backbone, because the language model is kind of the reasoning engine of all of that. It's the one that is trained on huge amounts of data, right? And then they take the image model that also provides actually very good, very capable representation. And in the first stage, they used a set of training data such that they just align the image embedding with the language embedding, right? So that your image token and language token live in the same embedding space or semantic embedding space, right? And so what they do is, again, they first align the image embedding with the language embeddings, and then they have a data set on which they train the whole system end-to-end using fine-tuning techniques, right? And fine-tuning, there's various techniques for fine-tuning, low-rank adaptation and things like that. But the key trick is that this overall training requires far less data than that went into these individual modalities that were being trained, right? And there's now a whole community that is looking at these, what's called multimodal large language models. This is taken from a recent survey, if you want to. It's a very nice paper that summarizes kind of what's going on. And this is just expanding on that idea where we take the input are these individual modalities like images, video, audio, and then we first project them into a language space, right? Just like what the Lava model is doing. And you can use many different kind of backbones for that. It doesn't have to be one specific one. And then on the output side, they also then train it to output text, like for images, for example. But now the most recent work is also moving into, even on the output, we're connecting it to diffusion kind of models. So that on the output, it's not just text, but you can generate videos on the output side. And they do that through a similar alignment process, right? So if we now come from a robotics perspective, if we now add, let's say, robotics data to this kind of mix, then maybe there's a hope that we can learn capable models without needing the kind of internet scale data that the language people have at their disposal. So that's why I'm hopeful that we can make some real progress here in this domain. And with that, I want to summarize briefly. So, okay, we've seen, in the interest of time, we've seen huge progress. We're still not there yet. I think simulation, there's various ways in which simulation can help, and I'll leave the details here to the discussion. I think another aspect that we really have to look into is benchmarking, because right now, a lot of the work is kind of showing videos rather than showing really capabilities of these models. I think simulation can make quite some contributions to that. And I think going back to RobotGPT, I think we're still not there yet, clearly. Still a way to go. But I think generating large demonstration data in simulation, combining that with real-world demonstrations, and then mixing this with all these other existing models, right, to train end-to-end systems, I think is, from my perspective, a very promising way to go. And there's many, many questions, of course, on how to specifically do this, like how do we get geometric reasoning capabilities that are better, what kind of data should we generate, how much do we need? I think I don't think anybody has really the answer to this question, like how much do we need, right? And how does the integration with the language and the robotic action work? And of course, in the end, it's clear that we will need real-world fine-tuning and learning and reinforcement learning for these robots to be really capable in the real world. So this pure behavior cloning is not going to be the end of the story. And with that, I'd like to thank you for your attention and, of course, all the people that were involved in this work at NVIDIA and UW and all the interns. Thank you.
I guess we are slightly over time, but we can take a couple of questions. And those who want to leave can feel free to leave the background.
I think, thank you for a great talk here. I think you showed exciting solutions from sim to real. Could you comment the other directions, like real to sim? How we close the loop, leverage some real data to improve a simulator, and
Yeah, that's a great question. I think right now, so we see a lot of work on training models for 3D asset generation automatic. My experience is that many of the assets that are being generated, they're not quite good enough for physics simulation. So they look very good and it's very exciting, but I don't think they're quite good enough for physics simulation. That's why, for example, we looked at this work with this URD former where we're explicitly generating URDFs and very simple shape models, but at least some that work with the physics simulation. And there's another interesting aspect also with respect to benchmarking, actually, that is related to this question, right? So if you want to use simulation, for example, to benchmark capabilities, how do you make sure that the insights that you're gaining from the simulation benchmarking, that they are insights that are transferred to the real world? And we can talk about some details about that, but there is some really interesting questions related to that as well.
Thanks.
I'm just curious, when you mentioned end-to-end vision language action model, actually vision language model is transformer based and the training robotic model is diffusion model. How do you combine these two models together?
Yeah. So the transformer model, the robot, it doesn't have to be diffusion. You can imagine various ways of doing it. One is you could discretize your output action space actually using a transformer. And you can also then, of course, you can use a diffusion process on the output side of your trained transformer, right? So the fact that it's a transformer model doesn't mean that it can't be also a diffusion process that you use on the output side. So you're referring to this slide, right? And even this simple step like outputting control is a really tricky question, right? Like at what level do you do control? At what frequency do you do control? Is it in the robot frame of reference? Is it in the camera frame of reference? All these kind of questions, I think, are still, there's hints on where people say like what works better than other approaches, but there's still a lot of work to be done. And for that, we need to just thoroughly actually investigate these questions.
Do you think which kind of microchip is the best for the edge computing? Which kind of microchip, GPU or?
Oh, of course.
Or S?
No, but I mean, nowadays you can, of course, for a lot of this perception-driven kind of robotics, you will need some kind of compute on the robot for reactivity, but also a lot of the compute you can maybe offload either to the cloud or to some desktop compute, and I'll leave it to others to judge at this point what.
Let's take last question.
To kind of piggyback on this question about the control stuff, you alluded to the control signals, can be extremely diverse, right? You can get at different levels of granularity, frequency, and I mean, maybe this is kind of my bias as a human. It's hard for me to interpret visually control signals, easy for me to interpret images, but it kind of appears to me that control signals are like a much less like smooth kind of signal to learn than images and language. So I guess the question is, like, do you expect, or maybe have you seen any evidence or can you conjecture whether these things that are so super successful in vision and language will ever kind of scale at the same level of data to that like multi-hierarchy, completely abstract, multi-embodiment control signals?
Yeah, that gets back to this also this notion of the things that are so easy to us, right? Like this spatial geometric reasoning. I think at this point, that leads to one of the questions I had, like how can we get these vision language models to become much better at geometric reasoning, 3D kind of reasoning, right? Because one of the problems, I guess, is that the language data doesn't provide the details, and even a lot of the vision data. Now, if you think about models like Sora that can generate scenes, that there's something 3D in there, right? But it's not quite the quality that we need for these robots. At this point, I think maybe we can get actually pretty far, but we will need, I think, a lot of data. But maybe to train these 3D capabilities, that is where I think simulation can really shine, because we can generate a lot of this variability. So we did, for example, one line of work, MPyNets, where we trained a policy. So for this motion generation, for a manipulator, right? Like you have a cabinet or something and some obstacles, and you just want to reach a point without colliding. And you do planning in this joint space, and I showed this robot techniques. So what we did there is, for example, we generated a data set with, I don't know, let's say 1 million examples of reaching. And then we were able to train a network that actually can compile that into a policy that just takes in the point cloud and a goal, and it can kind of move the arm there pretty smoothly, and also in a way that is not just local, right? Kind of it learned some global kind of collision avoidance kind of notion, and I think that's similar for us humans. For us, it's really easy. But I would actually imagine that many of the models right now that we are seeing, and also, for example, like the RT models and things like that, that they would not be able to solve that task because they're mostly doing just free space reaching, right? But even the simple thing of reaching around obstacles and stuff like that is something that the current models don't have. But I think, again, with sufficient data, I would hope it might come out of it. God, it seems so easy, right? So.